So here in section 7.6, we're going to look at integration, not so much using tables, but computer algebra systems. So for example, let's say that we want to integrate 1 over 1 plus 2x dx. Well, I look at this and I see a function on the bottom. Its derivative is just 2, and I've got constants on the top. I could multiply by that 2 and then compensate outside with a 1/2. So then I could let u equal 1 plus 2x, so that my du would just be 2 dx. So here's my 2 dx on the top, and here's my u in the denominator. This is just 1/2 integral du over u, which is 1/2, and then the antiderivative of 1 over u du is natural log absolute value of u, and then plus a constant. And we just have to plug our u back in. So this would be 1/2 natural log, absolute value of 1 plus 2x is our u, and then plus a constant. So let's go ahead and compute this in Wolfram Alpha. So if you just do a Google search for Wolfram Alpha, this should come up. And we want to do calculus and analysis. So we'll click on that. And then you'll see integrals right here. So we can just compute an indefinite integral. That's what we want to do. Let's go ahead and click on that example. Now it pops up for me to try and use textbook math. I did not have real good luck with that, so I'm just going to type this regular. So we want to type integrate, tell it what we wanted to do, and then 1 divided by 1 plus 2x dx. So with respect to x, and I'm just going to hit enter. Now I want to make sure that it interpreted that property. Now it did 1 times 1 over 1 plus 2x. That's not what we want, so we need some extra parentheses in here. And now that's the output that we want, and we've got 1/2 log 2x plus 1 plus a constant. And we go back here, we had 1/2 log 2x plus 1 absolute value plus a constant. So notice here that it forgot our absolute value. So if I want to take this and bring it over, we just note that we really need the absolute value there. Because we want to expand the domain. We don't want to just have a domain where 2x plus 1 is greater than 0. So that basically gave us the same thing, except we needed the absolute values. How about this next example? Integral 1 over root x squared plus 2x minus 3. This was actually example 4 in section 7.3, and this is the answer that we got doing it by hand. Let's go ahead and put that into Wolfram Alpha and see what it gives us. So go back to alpha here. I want to erase that 1 plus 2x. And then square root, you type sqrt for square root, and then in parentheses I want x squared. So I'm going to use a caret for the exponent, plus 2x minus 3, and close up my parentheses and hit enter. And a double check here. Yep, that's what I wanted. So here we've got log root x squared plus 2x plus 3 plus x plus 1, and then a constant. So let's grab that and bring it over. Compare it. So these look like they're the same, except up here we've got a division by 2 in both terms. Well, remember that division inside a log is the same as subtraction outside. So we could combine these two together over the LCD of 2, And then that would be, log of the numerator minus log 2, but log 2 is just a constant. That would get absorbed by the plus c. So these really are equivalent. Let's look at section 7.2 example 3. So this was a trig integral. This is the answer that we got doing it by hand. Not super neat, but it's not terrible. Two cosine powers here. So let's put this into Wolfram alpha and see what we get. So it's a cosine cubed 4x. So I'll type my COS cosine. I'm going to use a caret cubed parentheses 4x. And then I'm going to tell it times. And then we needed a cosine 3/2 4x. Actually, this needs to be a sine out in front. Can change that. So a sine cubed times cosine caret, and I'm going to put some parentheses here, 3/2, because that's the power, and then it's also of 4x. Okay, let's see how that looks. That is indeed what we wanted to compute the integral of, and here we get this expression. So that's looking a bit messier than what we got by hand. So it popped it out of there pretty quick. There we go. However, it's not nearly as neat as what we got by hand. Both are correct, and I imagine that you could use some trig identities here to show that these two are correct. Remembering that this arbitrary constant on the end, the plus c, that will absorb other constants. So when you have identities like 1 plus tangent squared is equal to secant squared, the 1 out in front could get absorbed by that constant. So it makes things that don't look like they're the same really the same when the constant gets absorbed. So just something to keep in mind when you're working with computer algebra systems. It will pop an answer out for you real quick, but this is not really the most usable answer. It's not a really nice form for the answer, where when we did it by hand we got a nicer form. So sometimes you can do a little bit of additional work, and you can help the computer algebra system out. Wolfram Alpha is pretty high-powered computer algebra system, and actually the ones on the TI calculator are pretty good also. So you might try this if you have like a TI Nspire with a CAS. You could try that integral and see if it gives you a better form.